Great. So welcome everyone to this week's Math Physics seminar. We are delighted to have Daniel Sage from Louisiana State University. He's going to talk about meromorphic connections on the projective line. So over to you, Daniel.
Okay, well, thank you very much. I'm delighted to be speaking, I guess, virtually in Bangalore. Anyway, as Aswin said, I'm going to be talking about meromorphic connections on the projective line and with specified local behavior. So essentially the local to global question for connections on P1. So what I'm going to try to do is to give an overview of this problem for, well, of the case of rank n vector bundles. So a lot of what I'm going to say makes sense in the context of flat G bundles, or if you prefer G connections for reductive groups G. To do that requires introducing sort of lots more terminology and notation. So I'm only going to say maybe a few things about that at the end if I have some time. But anyway, we could remember that that does exist. Okay, so let me get started. Oh, and another thing, I'm a mathematician. I'm not so used to talking to physicists. So if I say some stuff that either you guys don't know, or conversely stuff that you know so well that I shouldn't be wasting my time on it, you know, feel free to chime in. Okay, great. So the basic question we're going to be starting with is, let's look at a, let's see whether I can. Just trying to get a spotlight going here. Okay, great. So is that visible for you? Okay, great.
Yeah, I can see it.
Okay, so we're going to be looking at essentially, we're going to turn into the language of connections in a second, but differential equations of the form x prime plus az of x equals 0. So in other words, first order linear equations, but systems. So this is a matrix equation. And we're going to assume that this equation is meromorphic, but meromorphic in the algebraic sense. So I would just want the matrix of my connection to consist of rational functions, not sort of meromorphic functions in the sense of complex analysis. Though, of course, you can consider these problems in that sense, but I'm more an algebraic geometer than an analyst, so that's why I'm taking this approach. Okay, so if one wants to look at this in connection language, it's just equivalent to this connection where one takes the matrix of the connection and, you know, gets rid of the differential equation and writes d plus a of z dz on a rank n trivial vector bundle on P1. So incidentally, essentially every vector bundle I'm going to write down is going to be trivial or trivializable throughout this talk. But again, if you want, you can extend some of what I'm saying to a more general situation. All right. So what we want to do is to sort of understand these differential equations or connections in terms of their behavior at bad points. And so what do I mean by a bad point? So a bad point is a singular point, and it's simply a point where this matrix, the matrix of the connection, has a pole. Okay, so here's a very simple example, but it's one which, as we'll see, will turn out to be very important. We just have this anti-diagonal connection with a 1 and a z inverse, and I've taken one z out of here. So anyway, this has a double pole at 0. Okay, because you have a z to the minus 2 sitting there. On the other hand, at infinity, it also has a pole. So if you do a change of variables, u to z inverse, the connection ends up being this thing with a 1u, but still a du over u out here. So it has a simple pole at infinity. And so this local behavior is determined by the induced formal differential equation. So what do I mean by a formal differential equation? So essentially what we're interested in is, of course, to look locally, but since we're looking in the context of algebraic geometry, looking locally, well, in the Zariski topology, there's not really that many, the open neighborhoods are still too big. So if we were working in the context of complex analytic geometry, this would be, or complex analysis, we would just take a disk. But here we look at what's called the formal punctured disk at a singularity. So this is the algebra geometric object with one, which is an affine variety, with affine scheme rather, with a single point, and it's determined by its functions are just Laurent series in one variable, so spec of that field. Anyway, what does this mean in practice? It means that you take your matrix of your connection, which is, you recall, has rational functions in it, and you expand all those rational functions as Laurent series in the local parameter at your point. So z minus a if you're at a finite point, and z inverse if you're at infinity. So I just gave a little example here. If you have d of this matrix here, then at 0 the induced formal connection looks like this. Okay, and of course there are many formal connections which are not don't actually make sense as a global connection, because most Laurent series are not Laurent series of rational functions. Okay. All right. So of course, we're only going to be interested in these objects up to isomorphism. And so we need to know the correct notion of isomorphism. Well, the idea is just like in linear algebra, where, okay, you make some change of coordinates and a linear endomorphism, the corresponding matrix is now changed by conjugation. Well, here we do a similar thing. We take y, the column vector y equals gx. So now if you compute what x prime is, and you remember that when you're using the quotient rule on a matrix, you have to keep track of the order. You get x prime equals this minus g inverse g prime, g inverse y plus g inverse y prime. And so now this differential equation x prime plus ax equals 0, it turns into the following equation in y prime. So you conjugate your matrix A by your change of coordinates matrix G. And then there's this extra additional term, minus g prime g inverse. So there's a term that involves the derivative and is not linear. Okay. And so these two differential equations, or if you prefer, these two matrices, are called gauge equivalent. Okay. And they define isomorphic connections. Okay. Now, of course, the question is, what are the allowable changes of coordinates? It depends on the context. So if you're looking at global connections, then the coefficients of G have to be global regular functions on P1. Well, that means constants. So now you're just looking at change of basis matrices, or change of trivialization matrices, which are in GLNC. So now, of course, that means G prime is 0. You're talking a constant matrix. So G is just, so there is no nonlinear term, it's just conjugation. However, for formal connections, this is not the case. Now G is in GLN of the Laurent series. And well, now there's a lot more that you can do. Okay, so we're going to need to talk about, to try and understand about, well, isomorphism classes of formal connections, because that's sort of what we mean, what I mean when I say local behavior. So we're going to start with a very simple dichotomy. Oops, I lost.
Can I ask a quick question?
Yes, please.
So are we working with equivalence at the level of Lie algebra elements, or do we need Lie group elements here? Like, is G really in the group version
so it's so we're working, I mean, both, in some sense, both are involved. I mean, we're looking at equivalent Lie algebra elements, but of course, the set of group elements that are, it's the set of group elements that give the conjugation. So of course, that doesn't actually matter all that much, because, you know, for example, if, well, so if we were looking at SLN or PGLN, well, the conjugation action of GLN, I mean, it does factor through PGLN because it's the adjoint group. So in that sense, you can sort of understand most of what you'd want at the level of the adjoint group. But on the other hand, if you're not over an algebraically closed field, then the map from SLN to PGLN is not necessarily surjective. So now there's some differences involved. So the short answer is, well, basically globally, it doesn't really matter, but locally it does. Because of this issue that SLN, say SLN over the Laurent series, going down to PGLN over the Laurent series is not surjective. But in general, well, for what we're talking about for GLN, it's sort of the group GLN is, I mean, it really is just a Lie algebra issue.
Okay, thanks.
Mm-hmm. All right, so we're now going to try to figure out, so we're going to now do the sort of roughest possible classification of formal connections. So a formal connection is regular semi-simple if it is equivalent to a connection with only a simple pole. Otherwise, it is irregular singular. And this, well, can be a little confusing in practice because it's extremely easy to write down a regular singular connection, which is in a gauge that has nasty poles. You know, basically take an arbitrary, you know, connection matrix which has only simple poles, do a gauge change by something which has nasty singularities, and lo and behold, you usually get something with nasty singularities. So the point is, it's equivalent to something with only a simple pole. There are other ways to see this, which I probably will only get to touch on later because it ends up being a little complicated. But anyway, this is sort of the first and maybe most important dichotomy in the subject. Okay, and so now I'm going to state 3 questions which are going to model everything I'm going to talk about for the rest of today. So given a meromorphic connection on P1, okay, you get there's a finite collection of singular points and they have associated formal connections. So that's global to local. We're interested in local to global. So what about the other direction? We take a finite collection of points and corresponding isomorphism classes of formal connections. And now there's three sort of obvious questions. The first one, does there exist a global connection such that the singular points are precisely the specified points and the induced formal connections lie in these isomorphism classes? The second question is a uniqueness question, which is usually called rigidity in this business. If such a meromorphic connection exists, is it unique up to isomorphism? And if so, it's called rigid. And actually, as it turns out, there's going to be a weaker version of rigidity called cohomological rigidity, which I may talk about later, which means not that it's unique, but that there's sort of no infinitesimal deformations of these things. So in other words, basically, you have a finite number of them. And then the third question is about moduli spaces. Is there a reasonable moduli space of meromorphic connections with this local behavior? And now you might actually be sort of wondering, why I've phrased these three questions in this way. In some sense, you might be saying, well, isn't the question, well, is there a moduli space? And then one can ask, is that moduli space non-empty, or is that moduli space a singleton? And the reason I'm writing in this way is that even though these questions sort of get, in some sense, from what sounds like easiest to hardest, it's actually, in some sense, the other way around. Like 3 is far easier than 2 or 1. As we'll see later, I can write down moduli spaces, but actually figuring out what's going on in them is quite challenging. Okay. So I'm going to talk for a while about something which you may be familiar with. It's the regular singular case. So this is a very classical question. So classically, these problems were studied basically when all the singular points are regular singular. So again, remember, think simple poles in some appropriate formal gauge. So in this case, isomorphism classes of regular singular formal connections are determined by the monodromy. So let's remind you what this is. So let's write down a formal connection. And let's choose, suppose it's already in a gauge where the simple pole is manifest. Okay, in other words, we have this B0 dz over z, that's the residue term. So we have a simple pole, and then all the rest is higher order junk. Okay, so trying to figure out the formal isomorphism class of such a connection is a question in asymptotic analysis. So this is a very classical thing. To make things easier, let's assume that B0, which is just an n by n matrix with constant coefficients. Yeah, maybe I didn't make that clear here. The B0, B1, B2, these are all just constant n by n matrices. The z dependence is simply in the Laurent series. So let's assume that no 2 distinct eigenvalues differ by an integer. Okay, I am not, just to be clear, I am not saying you can't have eigenvalues with multiple eigenvalues. That's fine, but you can't have one. If 1 is an eigenvalue, you can't have 2 as an eigenvalue. That's the issue. So this is called non-resonance, and the reason for this is sort of hidden. It's when you try to do some algorithms to solve some problems in asymptotic analysis, you discover that things get screwed up if you have eigenvalues differing by an integer. Okay.
So, but you do want all the B's to be semi-simple?
Nope. Don't care at all. So I have no restrictions at all on the higher B's, And B0 is any matrix, semi-simple or not. Its characteristic polynomial does not have roots that differ by non-zero integers.
Okay. Okay.
Okay. So in this case, it turns out that the formal isomorphism class is determined in the nicest possible way. Just erase all the higher order terms. Okay. And you get something like this, d plus b0 dz over z. So if you now take the corresponding differential equation and let C be a fundamental matrix for it, say defined in a neighborhood of 1, then, okay, so now we do the usual thing with monodromy. We go around our singularity at 0 by just, analytically continuing. Oops, my spotlight disappeared, so I was drawing something that you couldn't see.
We can see your cursor, even if the laser is not
You can
there.
see the cursor. Oh,
yeah,
well.
yeah. So we see now the laser and the cursor together. Huh?
Well, then since the little menu, which gives me the spotlight, insists on being in front of the screen, which means I can't see what's behind it, I am just going to get rid of it and use the cursor. Okay, so as you analytically continue your fundamental matrix around this circle, you get a new fundamental matrix. And the new one in the neighborhood of 1 has to differ from the old one by a constant matrix. And that matrix is the monodromy matrix, e to the minus 2 pi I b0. And the conjugacy class of M parameterized this isomorphism class. Okay, so as long as we're in the non-resonant situation, the residue B0 determines the isomorphism class. And I'm going to call the adjoint orbit of this, so just the conjugacy class of B0, or if you prefer, the Jordan canonical form of B0, that will be what I call the formal type of this regular singular connection. Okay, if it's non-resonant, it's more complicated, but anyway, it is what it is. Okay, so now we're ready to start talking about our problems in this setting. So this is extremely classical. It goes back over 100 years. A system of linear ODEs is called Fuchsian if it is of the following form. So x prime plus, and then you have a simple pole at AI, at each of these little AIs. The residue at little AI is big AI. Anyway, and that's it. That's the differential equation that we're interested in. And why are we interested in this kind of differential equation? Because in this case, both the singular points and their residues are manifest from the matrix. Okay, we're looking at this, and you can see, it's easy to see that there's no singular points except at the AIs. And at the AIs, the residue, and hence the monodromy, is determined by capital AI, as long, of course, as we're in the non-resonant case. Okay, so anyway, as I said, we know all the singular points. So the one thing one has to be careful about is, of course, there could be a singular point at infinity. Its residue is minus the sum of AI. Now, of course, we can simply do a global, we can do an automorphism of P1 so that infinity goes to something which isn't infinity, and assume that we have no, that infinity is not a singular point. So we're going to assume without loss of generality that the sum of these AIs is 0, capital AIs is 0. If the residue is 0, then there's no singular point there. Okay, now I want to stress, this is a restriction of the regular singular problem. Not all differential equations with only regular singularities are Fuchsian. It just turns out that nobody seems to know how to address the questions I mentioned first in the non-Fuchsian case, when there's regular singularities which aren't, well, when the global differential equation isn't Fuchsian but has only regular singularities. Okay, so in this case, writing down the moduli space is really easy. So fix the non-resident adjoint orbits, then the corresponding moduli space of Fuchsian connections is just, well, you look at your orbits that correspond to the AIs. I mean, sorry, you take your non-resident adjoint orbits, you take a matrix, a k-tuple of matrix that are in these orbits. You require that the sum of AI equals 0 to guarantee that there's no singularity infinity. So that gives you something. And then, well, you look at conjugation by GLNC because, as we discussed, two connections are globally isomorphic if they differ by if their matrix differs by conjugation. Okay, and well, I mentioned something about for those of you who know something about symplectic geometry, this is actually a construction via Hamiltonian reduction. You can view O1 through OK, these adjoint orbits, as symplectic manifolds by their identification with co-adjoint orbits. If you take the symplectic manifold O1 cross OK with its GLNC action, that's a Hamiltonian action. The moment map is given by just the sum. So what we're actually looking at, this moduli space, is by definition the Hamiltonian or symplectic reduction at 0 of these things. Anyway, that's just a comment for those of you who already sort of are familiar with this kind of thing.
Daniel, just to repeat my question, I'm again confused by Lie algebra versus Reed groups. So the condition that sigma AI should be 0, that's a condition on conjugacy classes in the Lie algebra.
Yes.
Right?
Yes.
But maybe you're also imagining a similar condition on the monodromy matrices which live in the group, and that's where you're doing.
So, no, though that is also a perfectly reasonable question. So this is a moduli space where I'm looking at, it's a modification of the original problem I suggested. The original moduli space problem was about when two global connections have isomorphic local data, which, as you say, means that the monodromy should be conjugate. This is a variation on the problem where we're actually only concerned about the residues being conjugate. And you may be wondering why. Why do we do this instead of other things? Well, it turns out that especially when we move to allow irregular singularities, this is the kind of problem one knows how to answer. And the other one, the multiplicative version, is harder. Though in this case, not so hard. So yeah, your point is well taken. I'm always going, so in a lot of this stuff, there's additive and multiplicative versions of these problems.
Right.
I'm always going to be talking about the additive version unless I specifically say otherwise.
And
not because
is that also related to the resonant versus non-resonant thing, or is that a separate issue?
Well, it certainly is related because if you have, well, obviously, if I go back here, so let's forget about the asymptotic analysis, which allows me to reduce from here to here. Let's just assume we start out in this point with this kind of connection. Then obviously, if you have resonant connection, and let's just make it really easy. Let's assume that it's semi-simple. Well, obviously, when you exponentiate, you lose track of these distinct eigenvalues that were distinct only up to an integer.
Right.
And so,
Right.
yes, it's this resonance issue is very much related to the monodromy. The residue determines the monodromy, but the monodromy doesn't determine the residue. So yes, that is in fact exactly the issue. And it's why, for most purposes, it's fine to consider the residue. This allows you to work in a Lie algebra as opposed to a group, which isn't often easier. And then you can try to figure out the rest of the way at the end of the day. That's a great question.
Cool. Thanks.
Okay, so now let's talk about the existence problem for Fuchsian connections. And let's give a simple example, a really simple example. Let's take two singular points. Then the moduli space is non-empty if and only if the two orbits are the negatives of each other. I mean, remember, we're assuming that there's no singularity at zeros, at infinity, so obviously that's necessary. And of course, now one has the completely explicit solution. Well, you have one residue is A1 and the other residue is minus A1. So extremely easy. Now, I'm mentioning this case not because it's so significant, but because it explains why this kind of really obvious explicit solution is not something we want to consider. So notice in this case, well, if n is greater or equal to 2, there's always a lower dimensional version of this solution obtained by restricting to any invariant subspace of A1. For example, take an eigenvalue of A1. Well, of course, that's also an eigenspace of an eigenvector for minus A1. So we can reduce to that one-dimensional space. And now we've got a solution to the analogous problem in this one-dimensional space. So somehow, if we allow this kind of thing, we're sort of just understanding lower dimensional things in a higher dimensional version. So what we're going to want is this definition. A Fuchsian differential equation is called irreducible if the AIs don't have a non-zero proper invariant subspace in common. Okay, so if n is greater or equal to 2, this is always reducible. So now the classical additive Deligne-Simpson problem, which was formulated first by neither by Delane nor by Simpson, but by Kostov in the late 1990s, given adjoint orbits, determine, and he didn't worry about resonance or non-resonance because from a matrix theoretic point of view, it doesn't matter. Determine whether there exists an irreducible k-tuple, A1 through AK, where the AIs in the given orbits and the sum of the AIs equal to 0. So as long as the AIs are non-resonant, the orbits are non-resonant, this is precisely the existence problem for Fuchsian differential equations that I discussed before. Okay. See what we're gonna. Yeah. Okay. Let me mention just one thing here. So the original Deligne-Simpson problem was the multiplicative version here, where one took orbits in the group in GLNC, in group GLNC as opposed to Lie algebra GLNC, and then looked for irreducible k-tuples, just as here, except now the sum of the AIs equals 0 condition is replaced by the product of the MIs equals the identity. So that's when you were asking earlier, you asked earlier about why do I mean Lie algebra or Lie group? Well, the true existence problem is more the multiplicative Deligne-Simpson problem. Anyway, I mean, again, it's a little, well, anyway, it doesn't matter. Okay, so this problem was solved by Crawley-Boevey almost 20 years ago in terms of quiver representation. Well, actually, probably 20 years ago because the paper came out after he solved it. And I'm going to explain this at least a little bit because because it's interesting. So here's Crawley-Boevey's solution to this problem in terms of quiver representations. So a quiver is just a directed graph. And well, here's how you approach this problem. So we started with a k-tuple of adjoint orbits, O1 through OK. We define a quiver. Well, we need a few things. We need a quiver. We need a dimension vector. So this is just an n-tuple of positive integers, sorry, an i-tuple, where I is the vertex set of the quiver. I haven't explained that yet. And then a deformation vector, which is an i-tuple of complex numbers. So what is this quiver? For each of the orbits, well, I have a base point, and then I have a tail. One tail for each of the orbits, and the length of the tail is the degree of the minimal polynomial of O of I. Not the characteristic polynomial, the minimal polynomial. Okay, so these tails have different lengths. Now, I'm not going to go through the details are not so complicated, but complicated enough. The alpha i's are determined strictly by the Jordan block structure of the O of i's. They're actually involved the ranks of the O of i's, the rank, the ranks of products of powers of your O of i's, and the lambda i's are determined by the eigenvalues of the O of i's. Okay. So now we take the double of this quiver. All that means is, what's the double of a quiver? Anytime you have an arrow, you draw an arrow in the other direction, and you keep track of, like if there's multiple arrows in one direction, you keep track of which arrows in the other direction correspond to the other one. Okay, so and now we want to consider representations of this doubled quiver. What's a representation? At each vertex, you put a vector space. For each arrow, directed arrow, well, I guess arrows are always directed. For each arrow, you put a linear map. Okay, that's it. And we want the representation to have dimension vector alpha. That means that each of these vector spaces have the dimension given by alpha I, by the appropriate alphas. And then we want it to have this relation which says, well, at each vertex, you can get a endomorphism of the vector space at that vertex by, well, either going out along an arrow and then in along its dual, or out along a dual arrow and in along the original one. Okay, so that's what I'm doing here. These are the ones where you go out on a dual and in on the original, and you subtract off the ones where you go out on the original and in on the dual. So this is going to be when you add all these things up, this is an endomorphism of your vector space at the vertex, and we want it to be a multiple of the identity, namely, and the multiple is determined by this lambda I. Okay, so Crawley-Boevey then showed that irreducible solutions of the Deligne-Simpson problem are equivalent to irreducible, or are in bijective equivalence to irreducible representations of Q bar with a given dimension vector satisfying the deformation relations, these things, determined by lambda. So if you're familiar with quiver varieties, then, or quiver representations, then you know that this stuff over here are the irreducible representations of a certain thing called the pre-projective algebra. Anyway, So now for the last step, I'm going to sort of wave my hands even more than I already have. This quiver gives rise to a catch-Moody algebra, which is endowed with a collection of roots in z to the I. Remember, I is the number of vertices. The existence of irreducible quiver representation satisfying the given properties, these deformations, is characterized by being a positive root satisfying certain additional properties. And I should also say that Crawley-Boevey's work also solves the problem of when an irreducible solution is unique. So let me give an example or two of this so that we can see what's going on. Here, if we take n equals 2, so this is the, well, both of these examples are for n equals 2. And for convenience, I'm going to assume that the adjoint orbits are non-scalar so that the minimal polynomials have degree 2. Okay, a scalar matrix, of course, has minimal polynomial of degree 1. Okay, here's the k equals 2 case, two irreducible, two bad points. Okay, I'm giving you the 2 eigenvalues here. So in this case, we have the following quiver. I didn't draw the arrows on, but it doesn't actually matter for the solution. So the dimension vector that we're going to be interested in is 2, 1, 1. Here's what lambda is. It's differences between eigenvalues. Now, well, anybody who knows any Lie theory knows, this is the A3, this is the Cartan, the Dinghen diagram for for A3. Here are the positive roots. Alpha is not a root. And remember, we said before that the existence of irreducible quiver varieties requires you to classify alpha being a positive root satisfying certain additional properties. Well, it isn't. Alpha's it's not a root at all. Okay, so that's no irreducible solutions, and now we have a very fancy way of explaining that obvious statement that I had a couple slides ago. But for k equals 3, this problem is already hard. So if you want an exercise for the rest of the talk, try explicitly understanding what's going on. Take three adjoint orbits, 2 by 2 matrices, and try and figure out precisely when you can find a tuple with the AIs having the given Jordan forms and with them adding up to 0. I'm not saying that you can't do it, but it's not something that's so easy. Anyway, here's the point. Now our quiver looks like this. Okay, so this is the D4 quiver. Here's the dimension vector and the deformation vector. In this case, I've written out all the positive roots, but you can look it up in any book of Lie theory or Wikipedia or whatever you like. As you see, 2, 1, 1, 1 is the final. I mean, it's sitting there. It's a root. It's a positive root. Now, for existence, we also need certain conditions which you can work out to be the dot product of alpha and lambda is 0. But for all other positive roots, beta dot lambda is not 0. Well, this alpha dot lambda equals 0 translates into the sum of the traces is 0. And an irreducible solution exists and is in fact unique if, well, the sum of the traces is 0 and the sum of any 3 eigenvalues, 1 from each OI, is non-zero. Okay, it's pretty easy to figure out from the general, from Crawley-Boevey's general solution. Anyway, so that's that.
So more generally, is there also a distinction between what I call real roots or pure imaginary roots in isomorphic case?
So yes, this arises when I said that. Okay, I know you can't see it when, or maybe you. No, okay, I was pointing, but okay, maybe I'll use the cursor. The fact that this solution is unique comes from the fact that alpha is a real root, a real positive root. If alpha was an imaginary root, you would not have uniqueness. So yes, absolutely, this matters. Okay. So
just a quick question. Maybe it's not a good question. Can I still ask a quick question?
Yeah, of course.
Please go ahead.
How do you calculate the dimension of the moduli space?
So I don't think that I'm not sure that that is actually known in general. I could be wrong about that. It's certainly not in Crawley-Boevey's original paper, as far as I know. So, I mean, it's a good question. I just don't know the answer.
I think if you can somehow argue that the moduli space is non-empty, then there is a expression for the dimension, again, in this sort of quiver language, this natural quadratic form.
I mean, I would not be surprised. I mean, there certainly is. Yeah, I mean, I wouldn't be surprised. I just don't know it offhand.
Well, just a dimension of the moduli stack of the symplectic reduction, exactly as was said previously, just a very general thing which can be computed in terms of for the pre-projective algebra. Yeah.
Okay.
I think it's in Crawley-Boevey in one of his papers. Yeah.
Okay, great. I mean, one certainly knows as I said, I wrote down the moduli space before. So if he has a formula for that, which I wouldn't be surprised at, it's just not in the sort of, I don't think it's in his original paper on the subject. But yeah, it does not surprise me that it's known. All right, so wow, I've spent almost all my time talking about the tame case. So let me try and maybe speed up slightly. So you made a mistake telling me that you know, 75 to 80 minutes. So now I've just managed to extend what I usually talk about in half an hour to 50 minutes.
No problem.
Okay. Anyway, so let's now switch to irregular singularities. And so the first thing we need to know or need to talk about is, well, how does one understand isomorphism classes of irregular singularities? And so it turns out that formal connections have a have a Jordan decomposition in the same way that linear endomorphisms had a Jordan decomposition. So it's called the level-Turton decomposition. So here's the idea. Any formal connection is isomorphic to a connection of the following form. So you need to introduce roots of your uniformizing parameter. So like 1 over b's, z to the 1 over b. Then you have a Laurent series in minus 1, well, actually a polynomial in minus 1 over b. The coefficients here, the di's are diagonal matrices. N is strictly upper triangular, and it commutes with each of these di's. So any formal connection is isomorphic, of course, after extending scalars in this way, to a connection which is upper triangular, and where the strictly upper triangular part is only in the residue term. And if dr is not equal to 0, in this case, we say that the connection has slope r over b. Okay, that's a it's an invariant. And the slope in this GLN case has denominator where the lowest form is smaller or equal to n. Okay. Now, by the way, I should stress that actually computing the level-Turton decomposition for a formal connection is not so easy. I mean, I know how to do it explicitly in many cases, but that uses, well, some other work which I may touch on later. Anyway, if one doesn't have to extend scalars, we call the formal connection unramified. And we view this connection here. So just what I wrote up above, but would b equals 1. We call that an unramified formal type. It's the version of, it's like the residue matrix we considered in the regular singular type. Note, and of course, unramified connections have integral slope, but the converse is false. It's perfectly possible to have, I mean, slope is sort of a very, I mean, it's a weak invariant. It sort of shows the worst part. It only reflects what's going on in the worst part of the matrix in some sense. All right. So now,
quick question. So
absolutely.
Is there a condition between d naught and n? The last two terms in that, like, do they have to commute
well,
with each other?
yes. I mean, so n commutes with all of the di's, including d0.
Oh, okay. Commutes with all of them. Okay.
Yes,
Good,
all of
thanks.
the di's. Yeah. Okay. So now I'm going to start trying to address those three questions I talked about earlier for unramified frameable connections. And then finally, I will turn to the ramified case, which is where essentially all of my work comes in. Okay, so let's let this script BR be the space of principal parts of order at most R. Okay. I suppose it depends how you define the order. Remember, I always factor out a z. So this means that you have a z to the minus r plus 1 is the start. Okay, so now this is, well, this BR space has an action of this group GLN of the power series. So this means n by n matrices with power series entries which are invertible and whose inverse also has power series entries. Okay. Anyway, so this acts on the set of principal parts. Basically, you conjugate. Of course, when you conjugate, because these are power series, things aren't going to get any worse than this z to the minus r term. You're not going to get anything lower. But of course, you will get junk higher in general. And so we just throw it away. We truncate at the residue term. So for those of you who are sort of used to this kind of stuff, you may recognize that if you don't want to talk about truncation, what you can do is you can view these as functionals and view it as the coadjoint action, as a certain coadjoint action. But anyway, to be sort of elementary, let's talk about conjugation followed by truncation. And for those of you who are worried about some infinite dimensional group acting, well, this group factors through GLN of this quotient ring, where things higher than z to the r plus 1 only affect things higher than the residue term, which gets truncated away anyway. So we actually are working through a group which is finite dimensional over C. So it's not that weird. Okay, so anyway, if A is an unramified formal type of slope R, we call the orbit O of A under this action. So then So then this unramified formal type is a matrix that fits into here. And we call this orbit the truncated orbit of A. And by the way, if R equals 0, we're back in the regular singular case. This is just the adjoint orbit. So again, although just like in the regular singular case, the reduction to Fuchsian connections was because you have this complication where it's hard to tell whether an arbitrary connection just has regular singularities. So one looks at Fuchsian connections, which are connections where the fact that all the singularities are regular is sort of manifest from the structure. Here we're going to do something similar. The unramified version of Fuchsian connections are what are called frameable connections. So here we're only looking at connections which have this following form: D plus, and then a, you write down the principal part at each of the singularities you want. So in other words, this is a set of connections with specified bounds on the degrees of the principal parts at each singular point AI. Again, we might as well assume that infinity is not a singular point. So we have to assume that the sum of the residue terms is 0. Okay. And now we can answer all these questions that we talked about before, or at least we can address them. So we fix unramified formal types, A1 through AK, at the singular points little a1 through little ak. And we want to consider frameable connections as above, which have the given formal types at the given singularities. And more concretely, this simply means that the principal part at little ai lies in, sorry, I don't know what, sorry, that's supposed to be O of AI, the truncated orbit at AI. Okay, so this has been studied going back to Boalch, which is actually earlier than Crawley-Boevey's work. So Boalch constructed this moduli space only under the conditions when all the leading terms of the AIs are diagonalizable. So just to be clear, what I mean by that is dr is diagonalizable. Okay. But that wasn't really necessary, and Hiroe Yamakawa in 2014 constructed this moduli space in general. I should point out this moduli space is not great. It's not even Hausdorff in general. However, if you restrict to the subspace consisting of irreducible connections, then this is what they call the stable moduli space, and this is a complex manifold. And so the unramified Deligne-Simpson problem is simply, let's determine when the stable moduli space is non-empty. And this was solved by Hiroe in 2017, building on early work of Boalch and Hiroe Yamakawa. The proof is similar to Boalch in that it involves constructing some quiver and then interpreting the existence of the desired irreducible connection in terms of the existence of an irreducible quiver representation. However, the quivers get much more complicated. I'm not actually going to give you an example beyond that, but anyway, it's sort of the same flavor. Okay, so now we're into my yeah, go on.
Question. So just to make sure I understand the ramified versus unramified terminology.
Yes.
Is it true that for regular singular connections, there's always you can always write it H equivalent to something that
regular singular connections are always unramified.
Okay, that was
because yeah, maybe I should have said this. A regular singular connection has level Turton decomposition, which just involves D0 plus n.
Right.
So there's you don't need to introduce roots of z to write that down. Okay. All right. So now I'm going to, I'm going to give a couple examples of ramified formal connections. These are, well, in part, especially this first connection is sort of what got me interested in the subject originally, because this comes up in geometric Langlands. It's a very important connection, which was the first and still one of the very few irregular connections for which the wild geometric Langlands correspondence is known explicitly. And it's sort of remarkable how many papers and books Katz wrote just about these two connections here. Anyway, so the Frankel-Gross connection for GLN, I say for GLN because you can write it down for, well, let's say for any simple group. Actually, you can do it for reductive groups as long as the derived group is simple, but anyway, doesn't matter. So what have I done here? You take the matrix of the connection to be this circulant thing where you have ones on the subdiagonal and a z inverse in the upper right. Okay. And the Airy connection for GLN is very similar. You just add an extra, you make it more irregular with a z to the -1. Okay. So for those of you who are wondering, why is this called the Airy connection? Well, if you write it down, if you write down the 2x2 case and then take that matrix equation and write it as a second order differential equation, well, lo and behold, the Airy differential equation pops out. The Frankel-Gross connection, again, if you look at the 2x2 case, can be viewed as a modified version of a Bessel's equation. So these are actually coming from sort of standard elementary differential equations. Anyway, here's the point. Neither is diagonalizable without passing to a cover. And I've just written down their level-Turton forms. I'm not explaining why I know this is true, but I do. So basically what happens is for the Frankel-Gross, you have this matrix which has all the nth roots of 1 down the diagonal, and then you multiply by z to the -1/n. So that says that this has slope 1/n. And it turns out that is the lowest possible slope that any such connection can have. And in fact, it's the essentially unique formal connection with that property. That's a fairly recent theorem for G reductive by myself and Masoud Kamgarpour. And then here is the analog for the Airy connection. Well, here it's just easy. You just multiply by another z. So this has slope 1 + 1/n. Okay. All right. So now I want to talk about ramified formal types. And so I said at the beginning, I'm trying to give an overview of some things. And because I'm giving an overview, I won't have time to really explain a lot of this stuff in detail. It's sort of a separate talk, but I'll try and explain at least what we need, and then assert that I know how to do this. So to allow for ramified singular points, we need a notion of ramified formal types. And the problem with the level-Turton form is it requires passing to a cover of the formal puncture disk. It requires adding these roots. And if you're trying to do something like, so when I wrote down these frameable connections here, if I would like to do some example, something sort of like this, but with ramified things, ramified connections, well, it doesn't really make sense for me to say, okay, I want my level-Turton form to sort of be conjugate or gauge equivalent to something in here, because level-Turton forms can't be, for ramified things, can't be written in this form, because these have no roots of Z, and one doesn't want to introduce roots because now it doesn't look like a connection which is rational in the sense that it doesn't require roots. So anyway, the level-Turton form isn't really what we need. What we need is a rational canonical form. So the level-Turton form is basically a Jordan canonical form for connections. For these moduli space problems in the ramified case, we really need rational canonical forms. So what else? So remember, we had this group GLN of the power series before. Well, we're going to want a certain subgroup P of that group. For those of you who know what that is, it's what's going to be called a parahoric group. So if you're familiar with parabolic subgroups for like GLNC, so these are things which contain, say, an upper triangular. These are subgroups which contain an upper triangular which contain the upper triangular subgroup or conjugates thereof. A parahoric is sort of a similar thing. It's a group which contains, well, upper triangular mod Z. I'll be explaining this later. Maybe I shouldn't get into the weeds here. Okay, and then we want a filtration of, sorry, I wrote GLNC, but I really meant GLN of the, I guess I can write. I don't have to just say. It's not working. GLN of the Laurent series, sorry. By Lie algebras, which are where the zeroth term of the filtration is this thing coming from the parahoric. Now, maybe I should explain, hold on. Why are you suddenly talking about filtrations? There were no filtrations earlier. Well, yes, there were. They were just so obvious that one didn't need to talk about it. We were looking at GLN of the power series. Its Lie algebra is little GLN of the power series. And the associated filtration is just, you take GLN of the power series and you multiply by powers of Z. And this filtration is basically telling you what is the lowest degree of your matrix. It's the degree filtration. Okay, so it's a very sort of simple, obvious thing. For ramified singularities, you need, well, these more complicated filtrations. We need an analog of BR. That's the principal parts of bounded degree. Well, how do you write down principal parts of bounded degree? Well, that's like you take GLN of the power series, you multiply by, say, Z to the minus R. But then since you want it truncated, you then have to throw away the positive things. Well, that's what I did here. I said we want something like the P to the minus S, so the minus S step in the filtration. Then you throw away the quote unquote positive stuff. And that's what we want. And this, again, has an action of the group P, the parahoric group P. It acts on P to the minus S, just by conjugation. This introduces stuff higher up in the filtration, which we don't want, but we're modding out by that, so that doesn't matter. So you're truncating. So again, this is truncated conjugation. And then finally, we have this truncated orbit, O of A. All right. And so now, okay, there's a lot of technicalities here, so I now want to reduce to this sort of simplest possible case, but it's a very special case. So I'm only going to talk for the rest of this talk about maximally ramified singularities. So a rank n formal connection is called maximally ramified if its slope is r over n. And we need r and n to be relatively prime for some technical reasons. So for simplicity, I'm just going to talk about n equals 3. And okay, I'm going to write down this particular matrix omega. So omega inverse is the matrix of the Frankel-Gross connection that I talked about earlier. Okay. Now here, omega is regular semi-simple, but it's not diagonalizable over the Laurent series. That's because its eigenvalues are the cube roots of z. Okay, so you have to pass this ramified cover to get this. And for example, the level-Turton form requires passing through this ramified cover. However, it is regular semi-simple. That means that its centralizer is still a maximal torus, or Cartan subalgebra in the Lie algebra, by which I simply mean that if you pass to the algebraic closure, it is diagonalizable and just looks like the diagonal matrices. Okay. Now here is the interesting fact. So its centralizer turns out to be, you can write it down explicitly, it's just Laurent series in this omega matrix. Okay. And it turns out that any maximally ramified connection can be quote unquote diagonalized into this form, by which I simply mean there's a formal gauge change you can make that turns it into this form. And in fact, you can say more. A formal connection of slope r over 3 with r not divisible by 3 is formally isomorphic to d plus a polynomial of degree r in omega to the minus 1 times dz over z. In other words, I've just shown you how to write down a rational canonical form of such a matrix. So here is a way of writing down such a connection. Here's a way of writing down this connection without introducing roots, as the level-Turton form does. So now I can look at the space of rational canonical forms for these maximally ramified connections of slope r over 3. So that's what the r is coming for. And I'm going to view this thing as the space, so just the connection, but without the d, as the space of formal types of slope r over 3. Okay. So yeah, starting to, what is this? This is 75 minutes in, so I should probably not go on too much longer. But I'll maybe go a little faster and people can ask questions if they have them. So for maximally ramified connections, I want to explain, I have this list of what is needed. Well, I now want to explain. So now what I'm explaining is how you get these things. I've already told you what the rational canonical form is. What's the group, the parahoric group, and what's the filtration? Well, let O be the power series, so I don't have to keep writing it down. Let's look, so from GL3O to GL3C, we have the homomorphism, which just takes Z to 0, plug in 0. So now you can take the standard upper triangular subgroup and pull it back, and you get a subgroup I, which consists of matrices which are upper triangular modulo Z. In other words, things which schematically look like this. Okay, everything's a power series except the things down below, which are power series with no constant term. Okay, this is called the standard Iwahori subgroup. Its Lie algebra is the standard Iwahori subalgebra and looks just the same, but there's no invertibility requirements. And then what gets a certain filtration, which maybe I won't talk about now, but it's defined in terms of that matrix omega, which I talked about before, in terms of powers of that. Okay. All right. So now I can talk about what's the analog of BR. So we wanted principal parts of sort of order R. Well, the correct analog for maximally ramified connections looks like this. So polynomials in omega to the -1 of degree R, and where the leading term is regular semi-simple. Okay, and the rest, the other coefficients are diagonal matrices. So the group I acts on this space by truncated conjugation. And if A is a formal type, we can now consider the ramified truncated orbit O of A. Okay, so I know that this is a lot to throw at you if you've never thought about this kind of filtration before. However, the details don't matter so much. You can just sort of accept the fact that these exist. So now I can talk about ramified frameable connections. So this is the ramified version of Fuchsian connections or frameable connections. And, you know, this is maybe a little technical and I'm really running out of time. So maybe I will sort of skip it, but there's a notion of frameable global connections, and all the questions that we're going to pose involve global connections with a given ramified formal types, which are frameable. So just like in the Fuchsian case, we had to reduce from all connections with regular singular points to just the Fuchsian ones. Here we reduce to the frameable ones. It's essentially a way of saying that the singularities at each of the points sort of play with each other fairly nicely. Okay, so now I can state the general Deligne-Simpson problem, and that will probably be, well, it might be sort of the last thing I talk about. So here's the general case. We take arbitrary formal types, regular, irregular, ramified or unramified, anything you want at 3 given singular points. And now we consider frameable meromorphic connections with these formal types at the singular points. So this moduli space has been constructed. So by my former postdoc, Chris Bremer, and myself, when the irregular formal types are toral. What does that mean? It means that the leading term with respect to an appropriate filtration is regular semi-simple. So here, where I insisted that the D minus R was regular semi-simple, that's sort of where that's coming from, or an example of that. And again, I'm not going to tell you what the moduli space looks like, but they're constructed by Hamiltonian reduction, and they have this sort of general structure, sort of automorphic structure where you have some symplectic GLN-C manifold, which encodes local data at each point. And then you take the product of them. The moment map is the sum of the residues, again, just like in the tame case. And so now you just do Hamiltonian reduction by the GLN-C action. So now the general Deligne-Simpson problem is to determine when the stable moduli space consisting of irregular connections is not empty. So now, because I don't really want to trespass on your patience too much longer, what I was going to say in the last few minutes was going to talk about these problems in a very specific case of which I call Coccidor connections. I won't explain why they're called Coccidor connections. These are connections with 2 singularities. Remember, in the tame case, the 2 singularity case was trivial and uninteresting. But here it already is not. This basically means you have a maximally ramified irregular singularity at 0 and a regular singularity at infinity. And these are very important. They come up, I mean, most of the work, sort of explicit work on geometric Langlands involving connections where you have wild singularities has looked at connections of this form. Not entirely, but most of it. So yeah, maybe I don't want to go into all this. So far there is no, well, let me say what's some things that are known about this. So I stated the Deligne-Simpson problem, but when you had maximal ramified when you have ramified singularities, there's no general solution yet. In fact, until fairly recently, there was only, there were no solutions in any cases. So fairly recently, I, together with Jacob and our collaborators, we solved this problem for these Coccidor connections that I just described. It doesn't use a quiver approach at all. Sort of write down the moduli space and just figure things out. And it seems unlikely that quivers by themselves will be enough to solve these ramified cases. I should also point out that, yeah, okay, I have examples, but I clearly don't have time to talk about them. We've also solved the rigidity problem for these Coccidor connections, at least when we have unipotent monodromy at the regular singular point. And so those connections I gave earlier, the Frankel-Gross connection and the Airy connection, those are actually rigid for all n. So that's actually explains why they've been so important in recent work in geometric Langlands. They're in some sense motivic, and rigidity is related to that. Okay, and then I wanted to make some final remarks talking about things that I didn't talk about, in addition to the things that I just skipped over and didn't talk about. So in my abstract, I mentioned G connections. And today I've talked entirely about GLN connections. So a G connection is a connection on a principal G bundle. So much of what I'm saying makes sense, the framework makes sense for G connections, where G is simple or semi-simple or even reductive. However, much less is known. So there's moduli space constructions due to myself and Neil Livesey, one of my former students. However, even formulating the Deligne-Simpson problem is sort of challenging. So it requires a theory for reductive groups of these things I call toral connections for, which is fairly involved. Yeah, I won't get into it. That's a whole nother story. But in particular, Coccidor connections make sense for any simple G. And so, for example, Masoud Kamgarpour and I have classified rigid homogeneous Coccidor connections with unipotent monodromy at the regular singular point. We also have computed the differential Galois groups of Coccidor connections. So a differential Galois group of a connection is, well, in the same way that a Galois group can be viewed as the symmetry group of a system of polynomial equations, differential Galois group can be viewed as the symmetry group of a differential equation. And so we've computed that. So one reason I haven't talked about anything for simple G besides GLN is it requires going into, well, it requires some introducing in more well, it requires introducing some methods from p-adic representation theory, which was sort of here, but I could sort of slough over it. There, it requires a certain amount of additional preparation, which is, it's not that it's so hard, but it would have taken even more time. Okay, well, anyway, I've gone over even the generously flexible time that you allotted me, so I will stop here.
Okay, thank you. Thank you, Daniel, for the wonderful talk. So let's thank Daniel first. People should go ahead and ask questions if they have any. I have a couple, but I'll wait to see if there are others.
Yeah, may I ask you a question? Are you
Yes,
talking
please.
about connections on trivial bundle or what?
Yes, so at the beginning, I said that all bundles, we're assuming that all bundles here are assumed to be trivial, with one exception. So anytime I'm talking about moduli spaces, the connections are on trivializable bundles. The questions involving rigidity do not require that assumption. So
okay, and as for your formulation of Deligne-Simpson problem, why you restrict yourself and other people too to the trivial bundle case? What's the problem?
So it's not, well,
from the point of Langlands, it's not natural to look for the trivial way.
Yes, I completely agree with that. So for example, I mean, so although a lot of my motivation to work on these questions comes from geometric Langlands, it doesn't mean that a lot of the work that other people have done is necessarily motivated by this. For example, I mean, Boalch and, well, Hiroe and Yamakawa are basically algebraic geometers. Boalch really comes from sort of differential geometry and non-commutative Hodge theory. And of course, the classical, the original sort of Fuchsian connection problems that existed long before, that was really a question about differential equations. So on P1, so that's where the trivializable comes from. So the reason we've been considering that has more been because that's the situation in which we know how to handle things. It's not because of some deep philosophical reason that we think, okay, only trivializable bundles are what one needs to think about. No, it's a practical matter in the same way that we restrict to frameable connections as opposed to all connections, because that allows one to construct explicit moduli spaces in a way which I don't know how to do in general.
And why don't you, and actually many other people, work with the moduli stacks so that you don't have to care about the construction? It's almost
again, this is a matter of explicitness. It's not that you can't do it with these moduli stacks, and in fact, many people do. However, the Delane-Simpson problem. So yeah, I should say that the problem formulated by, well, Deline and Simpson didn't call this the Delane-Simpson problem, but the original problem that they constructed, or that they came up with, it's a very explicit problem. Like Simpson's problem on the paper is actually, it's literally about, you know, invertible matrices in GLN whose product is the identity. It's not sort of formulated in some abstract framework. So I'm not saying that there aren't other version. I mean, so here is a perfectly, I mean, here's an excellent question. Given a collection of formal isomorphism classes and a collection of singular points, does there exist a vector bundle, you know, a connection on a not necessarily trivializable vector bundle on P1, which has the given properties? That's a great question. You could argue that it's a better question than this sort of more specialized thing that we're looking at. However, it turns out that even in the regular singular case, that's really not what the Deligne-Simpson problem is asking. The Deligne-Simpson problem is asking the sort of more restrictive version of that question, which I've been addressing today. So it's again, it's not a, I'm not avoiding the general question for philosophical reasons. I'm doing it for A, for practical reasons, and B, because the original Deligne-Simpson problem is also this sort of restricted version of that problem, of the sort of the general problem, even in the regular singular case.
I think it's quite natural. It was a Delane question to Simpson after his work on 21st Hilbert problem about the existence of the connection with prescribed monodromy. And so then you prescribe the local monodromies for the regular singular connection about some given points, and then the question is whether it exists. So then that's exactly probably what he had in mind. And you can reformulate it, of course, pure algebraically in terms of for CP1, of course.
Sure.
For further curves, such a connection for higher general, it's obviously exists, but for CP1, it's non-trivial. Yeah.
Yeah.
Yeah. Okay. Thank you.
You're welcome.
I have a couple of questions. Can I ask? First is the Airy connection. If you know,
Yes.
if you know the existence, the moduli space is non-empty, does it help in the actual integrable systems? I think you mentioned it, but I missed that.
I suppose it depends what you mean by does it help.
I mean, does it give you the, I mean, knowing the moduli space explicitly, does it mean you know all the solutions of the integrable systems?
No. So I mean, one of the aspects of, well, you know, often the algebra geometric approach to studying differential equations, you know, D modules, is in some sense you're studying the differential equations without necessarily studying the solutions, because the solutions are, of course, usually not algebraic. So, I mean, I can tell you, so, okay, so for GLN, the moduli space of Airy connections.
Yes.
Well, of Airy connections, so there's sort of, well, there's the moduli space of Airy connections that look like the one I gave. There's a slight technicality there.
Yeah.
It's a singleton.
Oh, it's a singleton. Okay.
It's a singleton.
Okay.
I mean, that's what rigid means.
Rigid means. I see. Okay.
Yeah. In the so for GLN, so Kamgarpour and I have shown that Airy G connections are always rigid. And what this means in general is that the moduli space is finite. But in GLN, it turns out that that is equivalent to it being to the moduli space being a singleton.
Okay.
That's due to Bloch and Hainaut. So
my question is,
knowing the moduli space doesn't actually tell you anything about the actual solutions, because, for example, well, the Frankel-Gross connection, which I mentioned earlier, is also rigid. Also has it for GLN, the moduli space is also a singleton.
Yeah.
And so clearly, knowing that you have a point doesn't tell you much. Now you can get information about the isomonodromy integrable system of these things. So sort of understanding that aspect of things by constructing somewhat larger moduli spaces where the formal types are not completely fixed, but their combinatorics is fixed. So what I mean by that is, in the unramified case, this would mean that the degree of the principal part is determined, but not the isomorphism class of the principal part.
Okay.
So that's what I mean by combinatorics. And if you're, so I keep forgetting that I'm actually have a tablet here, so I could write something down. So you can have a situation where you have like connections with sort of given, say, local combinatorics. I mean, I know I'm not really explaining what that means, but so now you have two maps from this. You can go down to connections with given formal types. This is all up to isomorphism, of course. And then you can also have this map into sort of Stokes data, or if you prefer, generalized monodromy data. Okay, and the fibers here are the moduli spaces that I've talked about today.
I see. Okay.
But here, if you go in the other map, you get the leaf. So here, the fibers are the leaves of the isomonodromy integral system.
I see.
And somehow these fibers are essentially orthogonal to each other in a sense that can be made fairly precise. So this, from this kind of approach, you can certainly get some other interesting information besides the moduli spaces. You know, this information about isomonodromy and, you know, connections with Pain-Levé equations and all this kind of stuff. But you don't get any information about like solutions to the actual,
right,
you know, to the actual differential equations which are sitting there.
Okay. And one quick question: can all this be done also on genus G greater than equal to 2 surfaces?
So it. I mean, the short answer is, I mean, so there are a number of people who have considered this. So these constructions tend to be a little less explicit than the kinds of things that I've done. So there's a school of Japanese mathematicians. So Hiroe and Yamakawa are sort of part of it, who I believe have looked at these things. So, I mean, one of the things that I'm most interested in is the rigidity problem. I mean, that's sort of where I sort of started. It's one of the places where my interest in the subject got up because of how it connects with geometric Langlands. And unfortunately, one doesn't get, I mean, the rigidity problem doesn't really make sense for higher genus. So that's sort of why in essentially all of my work, I've restricted to P1. But I mean, these questions it's not that the questions don't make sense. It's just there's, haven't looked at it. I mean, I don't see why one couldn't, and certain other people have.
Thanks a lot.
Sure.
Yeah.
So I have a couple of questions, Daniel. So
Yeah.
In the regular singular case for GLN, there's this whole story of Katz's middle convolution algorithm. I think Crawley-Boevey and company also use some of that. So is there an analog of that in the irregular wild case?
Yes, definitely. So this has been, Arinkin has a paper where he essentially works out the analog of Katz's sort of rigidity algorithm. You know, a statement about, well, a connection is rigid if you can reduce it to, you know, an appropriate thing using Fourier transforms and middle convolution and stuff like that. So yes, it exists. It is actually I don't use it much in my papers simply because I'm often looking at things where I have sort of different, more explicit ways of approaching things. So, I mean, Bremer and I have this theory of what I was calling toral connections. And in the case of toral connections, one has lots of extra tools at one's disposal. And these tools are easier to apply in many cases explicitly. However, these things have been like there's work of Jive-Yun and his postdoc Konstantin Jakob, who use this kind of stuff fairly extensively, like to classify. I mean, well, Jakob has a paper classifying rigid G2 connections, and that, you know, that's not just a tame thing, that's a wild thing as well. And he's using, you know, Arinkin's work, which of course builds on Katz's work in a very you know, important way.
I see. And my other question was about Deligne-Simpson for general G, but still the regular singular case. I don't think even that has had I mean, that has been settled, right? That's also an open problem.
Yeah, I mean, as far as I know, so the one thing, so as far as I know, I've never even seen a paper which formulated it. I'm not saying that it's hard to form. Well, so for example, yeah, if I go back to beginning here. Okay, so this moduli space of Fuchsian connections, if you go to general G, the analog is pretty obvious, right? You know, now you have, again, you have adjoint orbits in the appropriate Lie algebra. You have, you know, the sum of AIs equals 0. You mod out not by GLNC, but by whatever group for your G connections you're looking at. So writing down the moduli space of Fuchsian G connections is no harder. Well, you have to worry about this non-resonant business, but let's punt on that for the time being. Now you have to figure out, what do you mean by irreducible? But again, it's there's in a lot of Katz's work, there's the notion of, I mean, he only worked for GLNC, but he has a notion of Lie irreducibility, which seems to be pretty clearly the correct version of this. Something about, you know, it basically means, you know, can you reduce to a non-trivial Levy subgroup, your connection to a non-trivial Levy subgroup? That's more or less what it means. So there, I've just given you a formulation of what the additive Deligne-Simpson problem should be for a general reductive G. But as far as I know, there's no solution to when, no known solution to when that is non-empty. Yeah, actually, when I first got interested in the subject, I was a little shocked by this, but you know, the thing is that Crawley-Boevey's work is really very strongly based on reducing everything to linear algebra, and it becomes harder to see what to do when, you know, you're looking at G2, say. You know, I've never sat down and actually tried to think, okay, for the symplectic Lie algebra, can one give sort of a quiver interpretation of this? I just don't know. But but I've never seen any papers on that subject. So for example, I mean, we have, I mean, Jacob and my collaborators and I, we have our theorem on this sort of special case for Coccidor connections. In the GLN case, we actually have very specific conjectures on what should be true for the analog for general G. And that's as far as I know, the only specific conjecture for the Deligne-Simpson problem for general G for any type of connections, tame, wild, unramified, ramified, anything. As I said, I don't know that I've even seen a formulation of the Deligne-Simpson problem written down explicitly in any case for other G. I'm not saying that people didn't know. I'm just saying that I've never seen anything written down.
I have another question, if I can. So this, I understand how this condition summation AI equals to 0 comes about. But
Yes.
if you relax that, is it possible to get a non-rigid, you know, get a moduli?
So if you relax that condition,
Yes. Supposing you thought of that a bit.
Well, the problem with relaxing that condition is that now you're not getting a connection. I mean, the problem is that the residue theorem has to apply.
Oh.
So if you relax the sum of AIs equal to 0,
yeah,
then by the residue theorem, all this is saying is that you have an additional singularity at infinity.
Infinity, yes.
with residue minus the sum of the AIs. And well, one can just do take an automorphism of the Riemann sphere
Yeah,
to move that to make sure that all the points are finite,
yeah,
and now you have the equivalent problem.
yes.
So
But
yeah,
on a genus G greater than 2, you cannot do that. Greater than or equal to 1.
right. No,
Yeah.
absolutely. There are differences in that case, but here it's not. Somehow it's not a different question. I mean, you could of course you could of course ask the algebraic question,
Yes.
where you just get rid of that sum of AI's equal to 0 problem, condition, but now it's not, it sort of has lost its relationship to connections.
Yeah. Got it. Thank you.
Mm-hmm.
Are there any other questions? Okay, so let's thank Daniel one more time. He was extremely patient in answering all of our questions. Thank you, Daniel.
And you were extremely patient with my going over.
No, that's okay. Thank you. Thanks a lot. So I'll
You're
go
welcome.
ahead and stop the recording. Yeah, people can hang around if you want.